Uh, Hello, everyone. Thanks for joining. Hi,
Hi.
Nathan.
Hi.
Sorry, feel like I was usually try to come 5 minutes early, but
No problem.
so now I feel like I'm late.
No problem at all.
So Nathan, I just made you the co-host, so you can share your screen. You might want to just try it out, make sure it works.
Okay, sure. Let's do this. Let's see if this works. Okay. Seems to work.
Okay, great.
Always reassuring.
Yeah, absolutely. So thanks for doing this, by the way.
Right. Thank you. It's really a pleasure to do that. I think it's very nice that you guys are doing this reading group. Well, not really reading group, but kind of concentrated seminar to learn a particular topic. Is this something that you do more or less every year, or?
Not, we usually have a seminar, but it's more, it's often more chaotic, like, how people get invited and who talks.
Right.
So, yeah, this semester, I'm trying to, for the people who have just showed up, I'm trying to invite a bunch of people to talk about on topics related to Benjamini-Schramm convergence, with an emphasis on graphs and surfaces.
Yeah, so the sort of Benjamini-Schramm stuff will be more apparent next week, basically. So today, what I thought I would do would be just to talk about sort of mixing times in general, because I don't know if this was a wise choice. It may have been, it may be that the better choice would have been to do a lecture on random graphs and the Benjamini-Schramm limit, but I don't know.
Yeah.
We'll talk about this next week, I guess. One way or the other, it has to be covered. Yeah, so I guess, so maybe I didn't realize, is this actually going to be the first talk of the series?
Yes.
Right, I see, okay. So, so I won't assume anything about Benjamini-Schramm limits then next week. That's
yeah, that's a good. That's good. So, okay, I guess it might as well be time to get started. So thanks to Nathanael Berestycki for giving the inaugural talk of the semester so the plan is to have a series of lectures on topics related to Benjamini-Schramm convergence, especially with a focus on graphs and surfaces. Okay, so I guess if you're ready, please go ahead and start.
All right. Well, so thank you very much Louis, for this invitation. As I was saying, I think it's wonderful. You guys are doing this seminar. Yeah, so today's lecture, in fact, is more related to mixing times and the cutoff phenomenon than really to Benjamin-Ishram limits. But I thought, because next week I will talk about random walks on random graphs and their mixing time, I thought it makes sense to first talk about mixing times and the cutoff phenomenon, just to introduce these ideas, because otherwise there'll be a lot to absorb next week somehow. So the idea is just to discuss this. So today, in fact, we won't talk about Benjamin-Ishram limits. So you'll have to wait for next week for that part. And so it's going to be just a sort of a gentle introduction. I'm not going to assume, I think, there's very little background in probability, and what I will assume I will describe. And the idea is to kind of explain these ideas in a friendly manner, and it only works if people do their best to ask questions and interrupt me when I'm going too quickly, or when there's something that's unclear, or something that's incorrect in your opinion, or whatever. So, right. So I'll start with a very simple, concrete, motivating example, which people like to talk about in this area. And it's, I think, the reason is that this is an experience we can all relate to. We have a deck of cards in our hands and we want to shuffle it. And you shuffle it a little bit, but your friend tells you, no, it's not shuffled enough. And the question is, you know, first of all, if you shuffle it enough, does the order become random eventually? Well, our intuition tells us that's the case. And so maybe a more interesting question, the second question is, you know, if that's really the case, that if you shuffle it many times, eventually the order of the deck become random, how many times should you really do it? If you want to have, if you don't want to, if you want to have a fair game, a game where you're not beating your friend. And sort of underlying these two questions, maybe more importantly, is how do you formalize something like that? So the first thing I'm going to do is try to tell you how we formalize that kind of questions. Then I'm going to tell you something about this question, which is the cutoff phenomenon. And then we'll talk about a few examples. That's the plan for today's talk. If there are questions on the chat, then please let me know, because sometimes I don't always see it. So maybe Louis, you can read me a question if I fail to see it. Thank you very much.
I will do that.
All right. So so let's start with how do we formalize that? And the idea is that we're going to have S is going to be a state space. Really, just I have in mind just a finite set. So, for instance, in the case of a deck of cards, you can imagine the symmetric group over 52 elements, the 52 cards. In which case, you know, so I encode every possible ways that the deck of cards can be ordered by a permutation of 52 cards, and just for future reference. Won't really need this, but what I have in mind is there are sort of two possible natural ways to do that. And one way is to declare that, you know, the permutation that I associate with a deck of cards is that I call sigma of I. You know, this is going to define a permutation. I'm going to call sigma of I the value of the card in position I. Okay, so that's going to be the convention that I will take. I could have chosen the opposite convention, but that's the convention I'm going to take. So we have this finite state space. This finite is just a finite set, and what we're considering is a Markov chain. So what is a Markov chain? That's a random process, x0, x1, ... So an infinite sequence of random variables with values in S. And the assumption that we make about this random process is that it's a Markov chain. So this really means, this is encapsulated by the following simple equation. It says, if I condition on the sequence of states that my chain visited. So x0 was equal to x0, dot, 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 and xt was equal to little xt. Then conditional on all this information, I give you everything about the past behavior of this sequence of states. And I ask myself, what's the conditional probability that in the next step, my chain is going to be in the state x little t plus 1? Then the Markovian assumption says that actually this probability depends just on two things, the last state and the next state. Okay, so all the extra information, all the other things that you've conditioned, all the other information that you knew, it was actually irrelevant. So maybe you knew the initial value of the chain, but that was irrelevant. The first state of the chain x1, that was also irrelevant. The only thing that mattered is the state that you were at the last step and the state you're trying to get to. So P of xy is the data that determines the transition of the chain. So it determines the probability, that we call it the transition probabilities of the Markov chain. And Pxy is the probability that if you're at x, the next state is going to be equal to y. And obviously it depends on the particular details of the Markov chain you're interested in. So for instance, in card shuffling, it depends how you're going to shuffle your cards. We're going to talk about some strange ways of shuffling cards in this talk because they're mathematically more convenient. But if your favorite way is to split your deck of cards into two and try to, it's called a riffle shuffle, and then put them together, then that defines a particular Markov chain, meaning that it defines a particular transition probabilities Pxy. Okay, so that's just the data that we start with. It's the Markov chain is defined by this transition matrix Pxy. Okay, so that's just the framework. And so here are maybe some nice examples, simple examples. So random transposition. So this is a stupid way of shuffling cards, but very convenient to describe mathematically. So what is the shuffle? We have our deck of cards, and I'm going to pick two cards uniformly at random in this deck and just exchange them. So mathematically, what I do is x is a permutation, and I'm going to move to the next permutation y with a probability which is just going to be equal to 1 over n choose 2, where if y can be written as x times the transposition ij. Okay, and here I and j are arbitrary. Okay, so that's one way of shuffling cards. Nobody would do that in real life, but it's actually I say that, but in reality, the theory was actually born because of this example. So there's actually an interesting story here. So this started in the late 70s in Bell Labs, and Persi, Diaconis, and Miraj Hashani were in Bell Labs and were kind of testing some properties of random permutations that they had proved. And they asked the engineer at Bell Labs to give them many to kind of generate uniform permutations and random uniform permutation, and try to test numerically the results that they had obtained. And it turns out that when they got the simulations from this engineer, the simulations didn't match at all with the results that they had proved. And so, well, they looked again at their proof, but the proof was actually correct. And so there was something strange about these simulations. So they went and asked the engineer exactly how he had generated the random permutations. And it turns out this was this engineer was kind of mathematically trained person, and he knew that it's possible to generate any permutation with a sequence of n transpositions. And what he had done was just composed n transpositions uniformly at random, and thought that this would describe a uniform random permutation. As we will see, this is very far from the case. And this is exactly what led Diaconis and Shahshahani to start thinking about this question of how many times should you run a Markov chain before it converges, before it's close to its equilibrium distribution. So I'm getting a bit ahead of myself because we'll define these things in more detail in a second, but that actually turns out was, even though it's a silly way of shuffling a deck of cards, it actually was the original motivating example of the theory. So that's random transposition. Here's another silly example that nobody would do in real life. You have your deck of cards sitting in front of you.
Nathaniel?
Yep.
I think you need the option of taking the same I, right?
Ah, right. Okay, good. Thank you very much. Yeah, so I wasn't going to get into that, but yes, you could also allow PXX to be the identity and PXY to be, I'll have to think about exactly what I'm doing. I mean, what I guess.
Yeah, but otherwise it's a bipartite graph, right?
That's right. So, okay, right, okay. What I could do maybe, okay, so let's do another version of random transposition. So with a prime here. And this, I will call it 1 over n squared with really I and j can be anything, including equal to themselves. Okay, and
so
then,
this just corresponds to sampling without replacing the same thing.
That's right. That's right.
And
Okay.
the dash
Good.
will
Very good that you're catching me on this, keeping me honest. Yeah, that's right. So it's actually a slightly better idea to consider that version than the one I wrote for kind of parity questions that will become okay. So otherwise, your Markov chain is, half of the time living on even permutation and half of the time living on odd permutation, which is an annoyance. Okay, very good, very good. So thank you. That's certainly an excellent point. So yeah, so what is random to Tom's? So this is the Markov chain where you have your deck of cards sitting in front of you, and you pick a card I at random somewhere in your deck, and you just put it on top of your deck. And so mathematically, what this boils down to is just multiplying by this permutation. And here I'm using cyclic notations. Okay, so that's another example. A third example that maybe is the simplest. That's not related to a symmetric group. So you have some graph, and here it is, and I don't know, something like that. Here's a graph, and the Markov chain is having values on the vertices, so it can be at any vertex of this graph. Let's say here, and here. And the Markov chain is simply defined by saying if you're at some vertex, then you're going to pick one of your neighbors uniformly at random and just jump there, as the next state. And so here, the transition probabilities for this Markov chain, they are very simple. The probability to go from x to y is 1 over the degree of x, provided that you can jump to x, so to y. So provided that y is a neighbor of x, or xy is an edge. Okay, so that's the random walk. Very good. So that's 3 very simple examples. So what is elementary theory for Markov chain? So this is something you learn if you do more than 3 hours of Markov chain, probably, and you can do that really in a very elementary fashion, knowing almost nothing about probability, or really barely more than linear algebra is needed. So the question is, we start from some state x, and the question is, what can we say about the law of the Markov chain xt at time t when t tends to infinity? So in other words, if I pick some arbitrary state y and I ask myself, what's the chance that I'll find a Markov chain in position y, starting from x, does this converge to a limit? And if so, what is it? As t tends to infinity. So one thing that should be clear is that if there's a limit, let's call it pi of y, then pi should be what's called an invariant distribution. What does that mean? It means that the probability to find the chain at y, how can I find it? I can imagine, let's ask myself, suppose t is very large, what's the chance the Markov chain is in y? Well, I can imagine where was the chain at time t minus 1, the previous step. Well, it could have been anywhere, but it might have been at x with probability pi of x, roughly pi of x, because t minus 1 is also very large, right? So the probability you would find it at time t minus 1 in x would be roughly pi of x. And then in order to go to y, you then have to make a jump from x to y with probability pxy. So if there is a limit pi, it's got to satisfy this identity. This is the identity that says pi is an invariant distribution. And the elementary theory of Markov chains says that actually, under very mild assumption, there is a unique invariant distribution pi. And in fact, the Markov chain, the law of the Markov chain, the distribution of the Markov chain converges to that distribution. So what are these mild assumptions? So the Markov chain should be irreducible. So what does irreducible mean? It just means it's possible to go from any state to any other state with some positive probability. That's it. So it's, there are no part of the states that you cannot reach. Okay, so that's irreducible. It's clearly going to be satisfied in all the cases we care about. So just with irreducibility, and because the state space is finite, there's a unique invariant distribution. And furthermore, if the chain is aperiodic, meaning exactly that it's not like this, you don't have the situation where half of the time the chain lives on half of the space and the other half of the time it lives on the other half of the space, then in that case you have convergence to this unique invariant distribution pi of y. Okay, so the limit as t tends to infinity, the probability to find the chain in y will converge to this unique invariant distribution pi of y. Okay, and so for instance, if you have a deck of cards and you want to answer question 1, which was if you shuffle your deck of cards many times, does it become random? Well, you've got to, for us, random, what it means is that the limits of this Markov chain is really the uniform distribution. And so in general, you would have to check that the uniform distribution satisfies this equation, and that would tell you that indeed your way of shuffling cards is valid. As t tends to infinity, your deck becomes more and more random. Okay, so that's what the elementary theory tells you. So here's an example where you can compute the invariant distribution. So if you have a finite graph, so I claim that the degree of a vertex divided by twice the number of edges gives you the unique invariant distribution. So why is that? So first of all, to check this equation, I can cancel out constants. So this equation is scale invariant. So this is a constant. I can ignore it. So I need to check that the degree of y is equal to the sum over x, so x in v, of degree of x times p of x and y. Right, that's what I need to check. But in fact, the probability to go from x to y will be equal to, just as I said, 1 over the degree of x, right, times the indicator that y is a neighbor of x. And so indeed, these degrees cancel, and I have just the sum over the neighbor of y of 1, which is indeed the degree of y. So indeed, that is degree of x, except for the constant factor, is an invariant, well, it's not a distribution, it's an invariant measure. And so I just need to check that in order to normalize it so that it's a probability distribution, I have to divide it by twice the number of edges, but that's obvious because if I sum all the degrees of every vertex, then I've counted every edge twice. Okay. So this really is the unique invariant distribution. And as you see, it suffices to check this equation because invariant distributions are unique. Okay, so far so good. All right. So we've got a good notion of what it means for the shuffling method to produce an ordered deck when t tends to infinity. And now the question that we want to ask, the more quantitative question that I asked at the beginning, how many times should you shuffle your deck of cards? Well, in order to answer a question like that, we need a good notion of distance. So I need to say something about how far the low of my Markov chain at time t is from its invariant distribution, from its equilibrium distribution pi. Okay, so for this, this is not a unique choice. There are many ways to do that, but this is a very nice choice. This is the choice of total variation distance. So if I have two probability distributions on the set S, I will call the total variation distance between these two probability distribution to be the maximum, or the supremum. Here it's a finite set, so it doesn't matter. And I just compare the mu probability of A and the pi probability of A. Okay, so I'm trying to find an event where the probability for mu of that event is very different than the probability for pi of that same event. Okay, so the distance is small, the total variation distance is small, if roughly speaking, the probabilities of every event is small. They're very close to one another. Excuse me. Okay, so the total variation distance is less than epsilon if the mu of A and pi of A differ by at most epsilon for every event. And you can see this is not a complicated thing to check. This is straightforward, really. That another way of rewriting it is the kind of L1 distance, except for a factor half between mu and pi. Okay, and as I said, it measures the maximal statistical error. So, right. So what you want to avoid is a situation where you think the probability of some event is very small, and I think the probability of some event is very high, and maybe I can trick you by taking advantage of that. Okay, so that's the idea of this total variation distance. So once we have this good notion of distance between probability measures, we can talk about the mixing time. So this is going to be the sort of the key concept here. So let's have a Markov chain S on some state S, state space S, where the invariant distribution is pi. So X is my Markov chain. So again, it's an infinite sequence of random variables in S, and pi of X, the unique invariant distribution. So what I can do is I will consider the total variation distance between pi, the unique invariant distribution, the limiting distribution for the random walk, and Qt of X, where Qt of X is the low of the Markov chain starting from X. What does that mean? I just ask myself, what's the probability that I find my Markov chain in some state A, given that I started from X? Okay, so the law in principle, it depends on X. The distribution of where I find my Markov chain, it will depend on where I started. So in order to avoid the question of where was the starting point, I will consider the worst possible starting point. Okay, so this is why I have a soup here. I take the worst possible starting point, the starting point which makes the distribution, the limiting distribution pi, furthest away from the Markov chain at time t. In many examples, many examples that probably will be of interest to people working in group theory, in fact, this total variation distance does not depend on X because of symmetry. So usually when one deals with a random walk on a Cayley graph, for instance, then where you start your random walk is kind of irrelevant because every point looks the same, right? So in many cases, taking the supremum in X is not needed because all these things don't depend on X. But okay, here in general, they do depend on X. And so we consider, just to be on the safe side, we consider the worst case scenario. We consider the worst possible starting point. Okay. So as I said, as t tends to infinity, the elementary theory tells us that this probability distribution is very close to that one. And S is finite. There's no problem in letting t tend to infinity. So we deduce that this distance d of t tends to 0. That's what the elementary theory tells us. So in order to define the mixing time, what I'm going to do is just this. I'm going to pick some epsilon between 0 and 1, and t mix epsilon. So the mixing time at level epsilon is going to be the first time, the smallest t, such that the total variation distance drops below epsilon. So epsilon, yeah, epsilon, I take it to be a number between 0 and 1. Why between 0 and 1? Well, 1 is the biggest value this total variation distance can be. Usually, if you start from a fixed point x and you're converging to an invariant distribution, then that total variation distance at time 0 is pretty close to 1 if the state space is very big. So it starts from the d of t is very close to its maximum, which is 1 at the beginning, and eventually drops down to 0. Okay, so it might look something like this. Here it starts at 1. Here it ends at 0, something like that. And the question is, what happens in between? Right, that's one way to think about it. And so t mix of epsilon is just going to be the first time I drop below epsilon. So I don't know.
Can't the total variation be 2?
Right. No, it cannot. So if you so there you can see it from the definition. So right. So both these quantities, they're positive and less than 1. So so your frequency is at most 1.
Thanks.
Or you see it with a factor half. Yeah, exactly. So it's not. It doesn't. It's a. I think because you had in mind the L1 distance. And
yeah. Thanks.
Right. So it's just a question of convention. And yeah, so elementary theory tells us, okay, if you go very far over there, this tends to 0, but how far do you have to go? And okay, that's the question. And epsilon suggests that it's a small number, but actually maybe it's not such a small number. Maybe you're interested in just 25% accuracy. I don't know, something like that. So here's the amazing phenomenon that was discovered by Persi, Diaconis, and David Aldous roughly at the same time and simultaneously and so independently, which is that in many cases, actually this mixing time does not depend on epsilon as n tends to infinity. So I'll give a precise definition, of course, in a second, because what we have in mind is a sequence of state spaces that become larger and larger, and as n tends to infinity, we see that this distance become closer and closer to the step function if you rescale it appropriately. And so, for a long time, the distance is very close to its maximum, and then all of a sudden, boom, something happens, and then the distance then stays very close to 0. So there's no point in kind of running your Markov chain for longer. You've already essentially reached your equilibrium distribution at that point. Yeah, so this is quite an amazing idea. I think the first time you encounter it, that many things could do that. And so that's the phenomenon. This phenomenon is called the cutoff phenomenon. I'm going to give a precise definition in a second, but that's the idea. Okay, so the idea is simply to say that there will be a well-defined time. This is going to be called the mixing time. You could take it to be mixing time epsilon with epsilon equal a half or a quarter or 3/4. It doesn't matter. Then if you rescale time by this quantity, the distance will look like a step function, dropping from 1 to 0. Okay. So Yeah, so two nice pictures of David Aldous and Persi Diaconis. Yeah, so probably many people have in this seminar have heard of them. I don't think they need much introduction, two giants of mathematics, really. So let me now give you the definition of a precise definition of the cutoff phenomena. And so the only thing that's a bit confusing is that we've got this sequence of state spaces. So Sn is going to be a sequence of state spaces. For each n, we have in principle a Markov chain on that state space Sn. You know, think the symmetric group on n object with n growing, right? That's obvious. And then, you know, we can do exactly the same thing as before. We can talk about d of t, except now it depends on n. That's a function which measures the total variation distance at time t between your Markov chain and its equilibrium distribution, but everything secretly depends on n. Okay, so the invariant distribution depends on n, the Markov chain depends on n, and so that's it, really. So once we have that, we can also talk about the mixing time for the nth chain at level epsilon. And so we're just simply going to say that there is a cutoff phenomenon if as n tends to infinity, the mixing time for level epsilon is very close to the mixing time for level 1 minus epsilon. So in order to drop below 1 minus epsilon, it takes essentially the same amount as dropping to level epsilon.
Is there a consistency between these various Markov chains in terms of the transition probabilities?
Right. So yeah, exactly. So in principle, in this definition, it's not, you know, it could be the nth chain and the n plus 1 chains maybe have nothing to do with one another. So it's, yeah, that's you know, in practice, we are usually interested with some concrete family of Markov chain, like, you know, we've got random transpositions with n cards, and n is growing, and, you know, the Markov chain for n and the Markov chain for n plus 1, they're related with one another. But in this definition, there's no such assumption. And it's not clear in general what it means, you know, how one should think about natural families of Markov chains that are related to one another.
May I ask maybe a silly question? Like in the picture you exposed before, I mean, is this ratio exactly? Sorry, not this one. Yes, I mean, there should not be like the ratio goes to 1. Shouldn't be like 1 divided by, so the time mix at, I don't know, epsilon very close to 0. It's almost 1, I guess. Yeah. And the 1 close to 1 is actually very close to 0. I was just checking. So the only time this can actually happen is just really one element, right? Just one epsilon. Is it always the case, or?
No, no, I'm not sure what you mean. So again, so the cutoff phenomenon would be saying that if you take, let's take epsilon equals 0.05.
Yeah.
So here's 5%, and here's 95%. Right. So this is here T mix of 1 minus epsilon, and this is here.
Oh yeah, okay, yeah, I see. I think I mixed up the x and the y axis. I was actually seeing the epsilon on the bottom one.
Right.
Now I see it.
Right.
Oh,
so
right, yes.
I'm very glad you asked this question. It's sorry, typical of the sort of things that when there are t, n, and epsilon, you can get mixed up.
Yeah. Okay. Sorry. Yes. So the epsilon is on the y-axis, and now this ratio really goes to 1. They're very close to each other, because on the other hand, you actually get a jump, right? So. Right.
And okay. So an equivalent way of saying, yeah. So as I said, an equivalent way of phrasing the condition that I was just saying is that really, if you rescale time by t mix of half, let's say,
all right,
quarter, it's not going to make any difference in the end. Then the limiting function is really given by the step.
Okay, right. Thank you.
Does that make sense? Thank you very much. I'm very glad that you asked this question. Okay, and so as I was saying, so there are several ways of phrasing this question. Another way is saying that yes, so there is this convergence to the step function, but concretely, one way is to say that let's call T mix to be the mixing time with epsilon equals a half. Okay, so you wait until you drop to halfway to the equilibrium distribution, to the invariant distribution. So you call that the mixing time, T mix n. And another equivalent way of checking that the cutoff phenomenon occurs is to say, if you wait 1 minus epsilon times this mixing time, then the total variation distance is still very close to 1. But if you wait just a bit more, so 1 plus epsilon times this mixing time, then this goes to 0. So this is encapsulating the convergence to the step function. Is that clear? That everybody happy with this, that these two things are equivalent? So I didn't say it, but d of t is in general a decreasing function of time. So that's why these two things are equivalent. Right, so here's some examples of cutoff phenomenon. The first one is that for random transposition, as I said, this was the motivating example. There is cutoff at a time which is roughly half of n times log n. Here n is the number of cards. The random to top example that I mentioned, which is you pick a card at random in the deck and putting on top of the deck. That has a cutoff at time roughly n log n. And here are some nice picture of examples that are very different from one another, so that you can see this is sort of somewhat ubiquitous phenomenon. So here is losange tiling. So we've tiled a portion of the plane using losanges. You can think of it also that we are looking at a room. This is the corner of the room here, and we've stacked cubes on top of one another. And there is a natural dynamics here, which is you can pick a cube and you can add it, or you can remove a cube if you can. So here's that defines a Markov chain on such configuration. There is also a cutoff phenomenon for this kind of things, which has very rich sort of connection with all sorts of things. This is equivalent to something called the Dimer model in statistical physics, and with connections to algebraic geometry and many, many things. This is a beautiful story. Here's something related to the easing model from statistical mechanics. You have, at every place in the square lattice, a plus or minus sign. You can think of them as being magnetic spin, and these flip depending on sort of magnetic interaction somehow between neighboring spins. It will take us a long time to discuss this, but it's now known that this, defines Markov chain for which cutoff was proved quite recently. So we sort of think this is a ubiquitous phenomenon for many, many chains. There are also counterexamples of chains that don't have that. So here's a simple counterexample. So if you have the d-dimensional torus of side length n, so let's let's do d equals 1. Okay, so here's the cycle with n point on the cycle. So what is going to be the mixing time? So I'm going to assume that you know something about central limit theorem and diffusivity of random walk, things like that. So if you have a random walk and it starts from here, it's going to take roughly n squared unit of time before it has a chance to reach the other half of the circle. Okay, so that's really what the central limit theorem is telling you. So you should expect the mixing time to be of order n squared, but the constant in front really will depend on epsilon. And that's because the random walk on the circle will converge when n tends to infinity to a Brownian motion on the unit circle.
So excuse me, for the lozenge tile, that says that with the cutoff phenomenon, if you run it a certain amount of time, then that surface, as n increases, will converge to some smooth object. Is that right?
Yes. So
And,
The cutoff
sorry.
tells you that this convergence occurs abruptly. It occurs all of a sudden. The fact that this surface converges to some limit, which turns out to be the uniform surface, if you like, that's something that is sort of elementary from the theory of Markov chains. Does that make sense?
Yeah, but it gives you a rate of convergence of the approximations.
Right, right. So I didn't say it, but the results that David Wilson proved, which is really an amazing result, gives you also some idea of what is the time at which the mixing, what is the order of the mixing time.
Thanks.
Yeah. So at least on a d-dimensional torus, you can't expect a cutoff phenomenon to take place, and that's really because there is diffusivity, there is a scaling limit which is Brownian motion, and somehow the issue is that this is not an issue, but what's going on is that this is sort of a low-dimensional example. So here are some problems which are like the most basic open problems you can think of. And these problems, despite 40 years of research, are to a large extent still open. What natural family of Markov chains satisfy the cutoff phenomenon? We don't have a good, even natural, nice, sufficient condition that guarantees cutoff. Related to this is, can you compute, or can you estimate mixing times? For this, we have much better tools that I'm not going to go into details, but I'll say something about some of the tools that go into this area. I'll just give you a glimpse of some probabilistic techniques, a glimpse of some group theoretic techniques, mostly based on representation theory. And I won't say anything about the analytic and geometric techniques. Maybe this was a bad choice of me, I don't know. Maybe you're more interested in the sort of geometric techniques. I don't know. Okay, we can't do everything. As I said, these are the most basic questions you can think of, given what I've just said, and these are to a large extent still open. And yeah, so I'll say maybe at the end I'll say something about this problem, this vexing problem. So let me tell you some probabilistic technique, which is based on two very simple ideas. One is something called the coupon collector problem. This is something you can do, you learn in the first course of probability usually, so it's really elementary stuff. So suppose you've got a company and they have capital N coupons, okay? So you're a collector and you try to collect these coupons, and you each time you go to a shop and you purchase them, but you don't see what they are. So they are equally likely to be one of those capital N coupons and independently from one another. So we assume that the coupon we acquire, they're independent at each acquisition and all uniformly distributed in a possible set of coupons so each of them with probability 1 over capital N. And the time we're interested in is how many coupons we need to buy before we've acquired the whole set. Okay, so that's the coupon collecting time, tau N. Formally, you just have IID random variables that are uniform in this set, and you look at tau N, the first N, such that the cardinality of the coupons you've collected, it's the whole set, it's capital N. Okay, and so the question we're interested in is, how big is tau N? When N tends to infinity, that's the problem of the coupon collector. And here's a simple answer. It takes roughly N log N trials before you've acquired the whole set. So specifically, if you divide by N log N, this converges to 1 in probability, but I'm not going to explain that. So how can you see this N log N come in? Well, let's think about how long, if I think, right, let's imagine I've already got I coupon, and I ask myself, how much longer is it going to take before I see a new coupon? Well, each time I sample from these coupons, from this set, I've got a fixed probability of seeing a new one that I haven't seen before. The probability will be n minus I over n. Okay, so probability is n minus I over n to see a new coupon. So expected time for new coupon, it will be just 1 over p. So it's just n over n minus I. Okay, so this is sort of elementary properties of random variables, of geometric random variables, but it doesn't matter. And so if I ask myself, what is the expected value of the coupon collecting time? Well, you know, I can just sum these things, right? It's a sum over I from I to 1 to n, probably 0 to n minus 1 of n over n minus I. And so you see that this is n times the sum over I, n times the harmonic series, so roughly n log n. And likewise, you know, let's not do the computation, but you can compute the variance, and you find that the variance is big O of n squared, so much smaller than n log n squared, meaning that the standard deviation is much smaller than the mean. Okay, so because of Chebyshev's inequality, tau n is very unlikely to be far away from its expectation. You know, to deviate by 2 standard deviation from the mean is already unlikely. To deviate by 10 standard deviation from the mean is very unlikely. So it would cost too much. It's too unlikely to deviate by epsilon n log n from the mean. Okay, so this is maybe a bit fast, but you can see that it does not require sophisticated arguments to prove something like this. I went a bit fast, but yeah, we just can decompose the whole coupon collecting time into time to collect the first coupon, then the second coupon, then the third one, and so on and so forth. And we can describe the distribution of these times very simply, so we can compute it basically. Right, let me tell you how we, given something like that, how we prove cutoff in some simple examples. So let's take random to top. So for random to top, what we do is I remind you, we just pick a random card from the deck and we put it on top. So how do we get cutoff for something like this? So there's 2 things we need to show. We need to show that if I look a little bit before the mixing time, then the distance in total variation is still very close to 1. I'm very far from having converged. Now, the reason why that's the case is that, so n log n is the tau n is n log n is the coupon collecting time. So that will be if you want, that's the time at which I will have touched all the cards in the deck. If I look before that time, so there are many cards that I haven't touched. And if you think about what's going on in my deck of cards, the cards that are at the bottom of the deck, they were not touched, right? So every time what happens is I pick a card and I put it on top. Those that are at the bottom of the deck, they have not been touched. And so they have kept their original ordering. Okay, so before that time, there are many cards that have conserved their initial ordering. And so if there's, let AJ be the events that the J cards at the bottom have, the fixed initial ordering. Okay, so J is fixed, and what I'm saying is that the probability that my Markov chain is in AJ is very close to 1 as n tends to infinity, if T is 1 minus epsilon n log n. Okay, because there are many cards that I didn't touch, and so these guards, they have kept their initial ordering. On the other hand, for a uniform distribution, this probability is just 1 over j factorial, because why should these cards have a specific ordering? You know, it's just any ordering is equally likely for the bottom j cards of the. So here I'm thinking of the relative ordering of these cards. Okay, so you know, for the uniform probability, to have a fixed ordering, it has probability just 1 over j factorial. So here's an event that shows that before time n log n, the two probability distributions, they're very far apart. Okay, so so we deduce that d of t is greater than 1 minus 1 over j factorial, and since j is arbitrary, this input. So okay, this is one way to get a lower bound for the mixing time. How do we get an upper bound? So this is, I think, a very nice argument. The idea is, again, to think about the coupon collecting time. So I'm going to have, you know, my deck of cards here, starting, let's say, from the identity. So initially, x0 will be the identity. And, you know, I will shuffle it using random to top. But what I'm going to do is I'm going to help myself by considering an other deck of cards, which is an imaginary deck of cards. But this one, it starts from already a uniform state. So I take a fully mixed deck of cards, one that has been mixed for time infinity. So there it is. And then what I'm going to do is at each step, for some reason, this is very annoying. Let me reshare my screen again, 1 second.
Oh, but by the way, I think you meant to say distance is going to 0 instead of distance going to 1 on this slide.
Here, no, I really meant distance going to 1. So we're still
I know that this one is fine. It's the next one that's
the next one.
Oh,
d1 plus epsilon n log n goes to 0.
Thank you. Thank you. Yes. Good. You're following, so that's good news. So we pick I at random, and what I'm going to do is that I'm going to put card I on top of the deck, on top of both decks. Okay, so card number I, it has maybe not the same position in both decks, but I will go and find it and put it on top of both decks. Okay, and then I do the same thing again. I keep going forever. That's what I do. So each of these deck, if I think of them individually, they're performing this Markov chain. They are, you know, a version of this Markov chain, just they have different starting points. And what is very good is that, you know, if a card has been called, then it stays in the same position forever after in both decks. Okay, because if I call it, then it finds itself at the top of the deck, and then what's going to happen next is that it's going to drop down, you know, as I call more and more things, and eventually I'm going to call it again and put it on top of both decks again, and again it's going to drop out. So once I've called it, the position of that card will remain matched in both decks forever. So what we find out is that at the time tau, where all cards have been touched, the two decks are actually equal. And because the one on the right started by being uniform, what you have is that the one on the left is also uniform at that point. So let me not write down in full details this proof, because we're very short on time.
Thanks. Very nice explanation. Just wanted to say so.
It's a beautiful argument. I love it. Yeah. So yeah, so this is the idea. This is what's called a coupling, right? This is
Yes.
Illustrates this very powerful idea of coupling of Markov chain. Right. I wanted to give a glimpse of what's going on. What's the connection with representation theory, which some of you may find interesting. So this shows up in this random transpositions, which, as I said, was one of the original motivating example for the theory. Diaconis and Shahani proved that the cutoff takes place at time 1/2 n log n. Again, the coupon collector problem can be used as a lower bound because now you're collecting 2 cards at a time. Okay, so the time to touch every card will be 1/2 n log n, roughly speaking. And before that time, there are just too many cards you haven't touched. And so the distribution is very far from being random. So the interesting part of the result is the upper bound, that after that time, the distribution is very close to uniform. And they made the following remarkable observation, that you can bound the total variation distance between a probability measure Q and probability measure, the uniform probability measure pi, in this manner. So this is a sum over all irreducible representation of the group. Here you've got the dimension. Okay, the sum is over all non-trivial, I should say, right? The trivial representation is excluded. Here you've got the dimension of the representation, and here Q hat of rho is just the Fourier transform of Q when you think of it as a function on the group. So this is really what this is not very complicated. You view Q as a function. I remind you that the total variation distance, you can think of it as an L1 distance. You apply Cauchy-Schwarz and it gives you an L2 distance, an L2 bound, and then you use Parseval identity to involve the Fourier transform. So it's not a very complicated thing, but somehow it brings you into a completely different realm, which is to try and say something specific in terms of representation. There's 2 miracles that happens in the case of random transpositions. One is that you can compute the Fourier transform quite simply. So let me not, because of time, I'm not going to explain this, so it's very simple. The Fourier transform of the probability distribution at time t is simply given by the tth power of the Fourier transform at time 1. And that's simply because you have the random walk this Markov chain has a product, it has a structure of being a product of IID random variables. And there's a second miracle, which is that because the probability transitions, they are constant over conjugacy classes of this group. Here, the probability to go from one place to another depends just on the fact that the difference between these 2 permutations is a transposition, and that's that's a conjugacy class property. That's a class property. And so because of that, there's a lemma called Schur's lemma, which tells you that the Fourier transform it has to be a diagonal matrix. So this matrix can be computed by taking traces, and you get a very explicit bound in terms just of something called the character ratio. So, okay, it will take too long to explain this, but this is a very, very, very beautiful idea, which was used in many, many examples. It's absolutely a remarkable way of approaching this problem. It turns out to be something that can be done in many examples, not in all of them, but in many of them. Okay, maybe because I'm out of time, I'll stop here. And thank you very much for your attention and your questions.
Okay, let's thank Nathanael. So, yeah. So are there questions? Yeah. If you have a question, just unmute your mic and ask.
So I seem to remember there was this statement by Persi that 7 shuffles gets you randomness. Is that connected to all of this?
Absolutely, yes. So actually, this 7 shuffle story is almost even more amazing than all this, because there's this particular riffle shuffle that people like to use, right? This is the one that I think professional card shufflers they tend to use. So you have your deck of cards, you split it into roughly 2, and then you try to interlace them in a way that is more or less random. So there is a convenient description you can make of this particular shuffle. It's a model, but it's pretty good. It's a pretty good description, I think, of reality. And what is even more amazing is that this shuffle, the total variation distance, can be computed exactly. I don't mean asymptotically, I mean exactly. So you plug in n equals 52 and you get an exact expression. And that is, I mean, it's just mind-blowing that you can do something like that. But of course,
indeed, yes.
of course, Persi is mind-blowing, so one should expect something like this. And so he was really able to compute it. You know, if you take a finite n, he will give you the exact expression, and it's something you can really compute on your computer like very easily. So because of that, he can tell you exactly how does it look like even for n equals 52. And it turns out the first time where this d of t drops below half is n equals 7. And that's where the n equals 7 comes. The number of shuffles being 7, that's where it comes from.
Amazing, just amazing.
Yeah, it's an amazing thing. It really is an amazing thing.
Thanks.
Yeah.
I just wanted to make a little comment, which is that normally when we play with measures, we don't care about L1, L2. It doesn't matter; they're all the same.
Yes.
But here it's crucial that if you look at the L2 distance between the measure and the uniform measure, there is no cutoff phenomenon. It just decreases, exponentially. I mean, there was some of exponentials.
Actually, thank you very much. This is an excellent point you raised, but actually it is not so. So, for instance, the proof that I just kind of very briefly flashed from Diaconis and Shahshahani, it shows cutoff also in the L2 distance. So what is going on? This is a very, very good point that you raise. So how is it compatible with what you're saying, what you're referring to, which is also true, that the L2 distance decays exponentially fast as t goes to infinity. And that's something that you can see from just an eigenvalue expansion, just standard spectral stuff. So it is true that the L2 distance, and in fact the L1 distance, would decay exponentially fast. But what it tells you, if you think about what this theorem tells you, the exponential decay either L1 or L2 distance, then bring up the picture. What it captures something here. It tells you this part of the graph is decaying exponentially fast. As you take t very, very, very large, but the chain is fixed. T is going to infinity, and this theorem tells you this stuff decays exponentially fast. It does not tell you, it does not tell you how that changes when you vary the Markov chain. When you start varying the Markov chain, you start getting new eigenvalues and a new spectral decomposition, and somehow you can apply the spectral theorem again, but the way the spectral theorem for the n+1 chain does not talk to the spectral theorem for the n chain. So this is a somewhat it's a somehow different feature altogether. So this is really an excellent point. I'm very happy you asked this question.
Well, I stand corrected.
No, it's a very subtle point. By the way, there is something that is interesting, which also we have no clue about, which is that when there's cutoff in L1, in total variation distance, there seems to be cutoff in other distances as well. It could be in L2, it could be in LP, it could be in other things, other senses as well. The mixing time does not have to be the same. It can be at different constants. It can vary by quite a bit, actually. But it seems that if you have cutoff in one, you also have cutoff in the other. And why that is, we don't really know. It really is a mystery. It's one of the many mysteries in this area. So the choice of distance, it's a choice, but it seems like the phenomenon remains the same, even if you make a different choice, although we have no, at least for many examples, you can always cook up bad examples where this fails, but for natural examples, it seems that it's true. And we don't have a theorem to explain that I know of, at least.
Yeah, I mean, this makes me think about Benjamini-Schramm convergence already, because you have this sequence of Markov chains. So I'm thinking about a sequence of graphs, and you're doing some random walks on the graphs.
Exactly.
I mean, anyway, so it's a sequence of Markov chains instead of a sequence of graphs, but still.
Yeah, so what I plan to do next week is to talk about random walks on random graphs that depend on n. And these random graphs have a Benjamini-Schramm limit. And somehow this Benjamini-Schramm limit can tell you something about the cutoff phenomenon for the Markov chain. That's what I plan to explain next week. So I don't know if there are some other questions, something like that, but no, okay, it looks like it.
Yeah, mostly it's just people just saying thanks.
Very good. I think there was somebody asking about the slides, and I'm happy to send the slides if to put. I don't know if Louis, you're collecting the slides or something like that, but I'm happy to send this to you. Or if anybody is interested in having the slides, then feel free to email me. I can also send them to you privately.
Well, would you mind? So I am recording this, but would you mind if we put it on YouTube? If you don't, I mean,
no, with pleasure, of course.
Okay, great.
All right. Well.
Okay, well, I guess if there are no more questions, let's thank Nathanael again.
Thank you very much. All right, yes, with pleasure. I will send them to you.
Yeah, thanks very much. It was a very enjoyable talk.
Thank you very much. Okay, so see you next week then.
Okay, so see you next week.
Bye-bye, everyone. Yeah. And thank you for tuning in at a different time than usual today.
Yeah, thanks.